My name's Robin Bell. I'm a geophysicist at Lamont Doherty Earth Observatory. It's part of Columbia University. And as Roberta just told you, Missy, Margie, and me, I know the English is bad, but me starts with an M. We're going to walk you through this. And I'm going to start by giving you a little background on a little bit about what I do, and then how the ice sheets are changing, just because it's a really simple message, and I think everybody should be able to explain how the ice sheets are changing. It's something that I'm terrible. I work it into a talk about almost anything. I don't quite tell my kids' teachers when I go to see them on Meet the Teacher Night, but if Meet the Teacher Night was a little longer, I probably would get there. So let's see. What are we going to do? We're going to start with, and first of all, I see we have some polar experts, so you guys are really lucky. You'll have to draw on them when we get into this. They'll be able to tell you their own experiences. But first of all, I'm going to show you a lot of stuff, but it comes from all sorts of different resources, and it's really just things that I show you are not really my work. They come from the entire community, both within the U.S. and globally. So I always like to acknowledge that what I'm showing you comes from a vast team of people. These are just a couple of my 3 favorite scientists in the middle of the East Antarctic ice sheet. But so there with that caveat, I always just like to show you this. So this is what I do. I work with a team of people. This is a subset of them. We take airplanes and fill them full of stuff. We hang things that look like coat hangers on the wings, and then we put other things on the end that look like little robotic arms on the ends, and then we fly over the ice sheets. And we use that instrument suite to measure what's underneath the ice sheet, because when you go and walk on top of the ice sheet, it's really kind of flat and boring. But underneath, there are all sorts of marvelous things to be found. So that's my research tool, and those are the people I'm lucky enough to work with. This is what it looks like when it's taking off. These are the coat hangers, also called folded dipole radar antennas. They basically use the same energy that's in a microwave, send it through the ice sheet, and that's a magnetometer, measures the Earth's magnetic field, so we can see where there are volcanoes and things. And inside we have we have one of these. It's a little fancier. We have a laser altimeter, only ours spins on a mirror, so we can map a whole swath underneath the ice sheet. And then we have a gravity meter, so we can measure the gravity field, and that tells us something about what types of rock are under there, because different rocks have different density. So that's my research tool, and this is one of my favorite images currently. We went to East Antarctica, I guess 3 years now, and we spent like 5 years trying to get there, and we had 3 weeks to work, because that's about the window you can work in when the temperature is above -50. Below -50, the planes don't work. People aren't very happy either. But we were able to, we had 2 planes, one from the U.S. and one from Britain, and we were able to basically send the planes equivalent to around the world twice in that 3.5 week period, and basically uncover this magnificent mountain range that's underneath the ice sheet. So this mountain range still gives me the goosebumps to talk about it. This mountain range is like the same size as the Brooks Range or the Pyrenees. Wow, I know. It's huge, but you can't see it. And these are like the first pictures really ever to see it. And as we were there, it was just marvelous, because we'd send the plane out, and it would come back with a profile, and the first thing you'd see is these mountains look really, really jagged. It's like, why are there jagged mountains underneath the ice sheet? And then even better, you can see there's a little bit of blue in the valleys. There actually is water down in the valleys underneath the ice sheet. So it was like all these marvelous things that we hadn't really thought would be there. The story gets better. The water's running up the hills underneath the ice sheets, but I don't think I have time to go into that, because I want to make sure you guys... You know what? You really want to know that? Oh, okay. This one requires 2 arms, so I can't do this and hold the microphone simultaneously. Okay, so what happens is you have water underneath the ice sheet. See, I really told you I needed 2 arms to wave. You have water underneath the ice sheet because it gets really thick, and the geothermal heat from the ice sheet, from the Earth's coming up, right? So it's minus 50 at the top. At the bottom, it's about minus 2. That's why there's water where the ice is really thick in the valleys. Okay, so there's water in the valleys, and this would be a normal river valley, right? So the water normally would run downhill. But we've smacked an ice sheet on top of it, right? And now the pressure is greater between my elbows, right? Just think about it. If this was really a piece of ice, the pressure would be greater between my elbows than at my fingers. So the water is going to get squeezed straight up the hill. It's kind of like you took a hose and you jumped on it. Or, as we've tried, if you took a Camelback, you know, one of those water things, and you drop a 20-pound bag of rice on it, you can get the water to run uphill. So that's what's going on. Whoops, I've changed. That's what's going on underneath the ice sheet. So there's amazing things happening on underneath the ice sheet that we really didn't know were happening before. So now we're going to get back to sort of the activity we're talking about today. Now you heard a little bit about what I do. Our planet, I like to carry our planet around. Here's our planet. Our planet has 2 poles, right? And 3 ice sheets, right? And they're really different, right? The northern one in this clever rendition is white. That's water. So that's an ocean. But we have Greenland up there. That's one ice sheet. On the other end, probably my favorite ice sheet. Oh, I don't know. Greenland's pretty. I didn't think I'd love Greenland, but Greenland's gorgeous. Antarctica actually has 2 ice sheets on it. Right. I know. It's kind of surprising. I didn't realize when I first started. Who would have thought? But there are actually 2. One is called West Antarctica. Very clever name. It's in the Western Hemisphere. And the other one's called East Antarctica. It's in the Eastern Hemisphere. But they're hugely different because East Antarctica is kind of like Canada, mostly kind of flat and boring, except for the beautiful mountains. Sorry, Margie's from Canada. It's good seeing my shoes taste so good. Anyway, so East Antarctica is pretty high geologically and has one big beautiful mountain range, the Gamburtzos. West Antarctica is much more like the Gulf of Mexico. It's mostly below sea level. It's mostly like a continental margin. So they're 2 really different pieces of ice. And they're going to respond to climate change very differently. It's kind of like, as I like to think, one is the freezer upstairs in your house, right? You know, pretty susceptible to what goes on in your house. East Antarctica is much more like the freezer in your cellar, if you happen to have one. You know, it kind of stays there, doesn't change as much till the power really goes out. You mean what's the geologically it's like? It's like a continental, it's like thin continental crust. Pardon? It's continental, this whole area, and I'm sorry for you guys who can't see, I'll run over there and show you. This whole area is West Antarctica. And if you took the ice off, it would still be below sea level, even after the Earth bounced back up.
So what about on the other side, on East Antarctica? What does that margin of what kind of plate tectonic?
Oh, the plate tectonic boundary is way the heck out here mostly. Antarctica is isolated, is surrounded by ridges. There's a little bit of extension going on here, but mostly Antarctica is kind of like Africa. Well, except it's not rifting down the middle, but it's mostly a piece of continental crust. And there's a difference between East Antarctica and West Antarctica tectonically, but they don't appear to be acting like different plates right now. They did in the past. That help? Or did I just confuse you more by? And did you guys get it? That this is basically, so basically this is what she was asking about. This is West Antarctica. Okay, so two poles, 3 ice sheets. Let's just sort of take a stroll through them. Here's Greenland. As I like to say, if you were to drop Greenland on top of New York, I know you guys are mostly from the West Coast, but you could do this too. You could figure out how big it is if you dropped it here in San Francisco. But if you dropped it in New York, where do you think the southern end of it would end up? How big do you think that hunk of ice is? Where? Florida. Other guesses? Close. Havana. It's a big piece of ice. I mean, you know, we always get confused because we use flat maps, you know. So to get back to Florida, and this is how much ice is in it. It's about 24 feet of ice, and we'll come back to sort of the impact of it. 24 feet of sea level equivalent if you melted it all and put it in the global ocean. So that's what it looks like in Florida. So now we're going to look at West Antarctica. And again, this is sort of, again, giving you a scale. You can see that West Antarctica is bigger than Texas. And it has a little less. If it melted, there'd be a little less of an impact. It's about 19 feet. There's about the same amount of ice, but since some of it's already below sea level, it has less of an impact because you're sort of filling in that ice space that's filled with ice with water. So that's West Antarctica. And then we're going to look at East Antarctica. And just to locate you, here's the Gamburt's Mountains are pretty much smack dab in the middle of East Antarctica. You can see why it was kind of hard to get there. So East Antarctica has an awful lot of water. It's 170 feet. It's a really old ice sheet. It's probably been mostly in place since we went from the hothouse to the greenhouse transition. So some parts of it have been ice covered probably for 34 million years. So this is the most stable piece of ice on the planet. And there's no 34 million year ice. There are people who are searching for the magical million-year-old piece of ice, but they're still looking for it. That's because it melts at the bottom, right? Remember how we were talking about how it's warm at the bottom? So ice sheets work where it snows on the top, and then it eventually melts on the bottom. So what's the mass balance? You'll often hear people talking about mass balance of ice sheets. And mass balance is really just like your checkbook. There's really not much fancier than that. People argue about the details about it a lot. But basically, ice sheets add mass by snow on the surface. That's your paycheck going in, right? And then the withdrawals pretty much happen two ways. Melting, right? Greenland's sort of the one you've probably seen pictures of, where Greenland melting on the surface. You know, the surface of Greenland in the summer is covered with these beautiful iridescent blue melt pools. And that's removing mass. That water's running off into the ocean. And then the other way you can remove it is by great big hunks of it falling off into the ocean. You don't actually have to melt the ice. When we think of, losing mass, it's not just melting. A lot of it just falls in the ocean. And when it goes from being, on the table to in the bathtub, that's when the water goes up. So that's basically all you need to know for mass balance. And that's my high-tech presentation of it, where the pluses are snow falling, and the two withdrawals are the melting into the ocean or the icebergs falling into the ocean. There's a lot of ice that's floating. Your question is just great. This is sea ice. This is the North Pole. This is sea ice. This is my friend who works on this. I tell her ice is just thin and skinny, and it's only like a couple meters thick maximum. And that's what you hear every year, and there's less and less of it. But this doesn't matter for sea level, right? Because this ice is already in the ocean, right? Doesn't matter what you do with the ice cubes once they're in the water. It's not going to change the level. Oh, it can change a lot of things. Albedo, salinity, lots of things. But it's not going to change sea level. And even this, this is sort of the iconic image of global change. This is even caught the scientists by surprise when this happened, was when this piece of, we always use small New England states, this piece the size of Connecticut, or maybe it was Rhode Island, anyway, broke off basically between Martin Luther King Day and the end of February. You know, this big piece of ice, again, this was a thicker piece of ice. It was 300 meters thick. But this also didn't make sea level go up directly, right? Because that ice was already floating. It was already in the ocean. It had another influence that I could talk about later, in that it was holding back the glaciers behind it. And so it was kind of acting like I'm always looking for the right analogy, so if you guys can help me find out the right analogy. Kind of like a bouncer, and, you know, keeping people from getting into a bar or out of a bar. And, you know, it's standing there, and it's keeping people from getting in or out. And once it steps aside, the other glaciers are going to start rushing in faster. So that's how it increases.
Wouldn't it be like a levee to a river?
Yeah, I just hate to use levees and rivers because it confuses people, because it's water again, right?
What year was that?
2003, early 2000s. Early 2000s. I could be wrong on the year. Early 2000s. But you just Google Larsen B breakup, and it might be in the paper we're going to give you. So basically, this is a concept I'm trying to get across, is that, you know, once the ice is in the cup, it doesn't matter. It's really how you get the ice in the cup that changes the level in the cup. We all know this intuitively. We just don't think it applies at a global scale. Physics happen to be the same, thank goodness. So these are the different pieces of ice I've been kind of walking you through. There's the stuff on the right. That's the sea ice, the scummy stuff that comes and goes over an order of a couple years. A couple meters thick. Polar bears like it, seals like it, penguins like it. The next piece are the icebergs. We talked about those. The next thing is an ice shelf. That's the bouncer at the bar. I really have to think of a better analogy. It's the anyway. I love any contribution to that. And then the thing on the interior, on your left, is the ice sheet. You can see this is where it's actually stuck right on the rock, and this is where, you know, it's maybe a couple 100 meters thick at the edge, but it can be thousands of meters thick in the interior. Now, one other tricky thing is it turns out that ice, this is actually something we've only discovered in the last 20 years. We used to think ice just kind of gooed into the ocean. You know, it was kind of like pancake batter, and, you know, it sort of just slowly ooze into the ocean. Turns out that there are these giant rivers of ice that move the ice really fast. So the ice here, where it's stuck to the bedrock, is going 1-2 meters a year, you know, maybe from me to them, right? Not very exciting. That thing called an ice stream, that's what we're going to be talking about. Pine Island is an ice stream or outlet glacier. Cleverly, we use two names to mean the same thing, just to confuse ourselves and everybody else. But that is going, maybe a kilometer a year, up to 12 kilometers a year. So just move, and those aren't tiny. They can be up to hundreds of kilometers wide. So understanding how those ice streams are working are critical to understanding how sea level will change. They're kind of the conveyor belt that's taking ice from the interior and cranking it into the global ocean. So the activity we're after today is understanding how those ice streams change. You know, we already sort of talked about one way, where the bouncer in the bar. And there's some other ways you can change how ice streams are going, or outlet glaciers are going. But that's the key. You know, melting's important, but in Antarctica it's not melting much. Greenland, there's lots of melt. You think of Greenland as sort of being the ice sheet where it wears a pretty blue necklace. But Antarctica, it doesn't get warm enough to do that. There isn't melt all over the place in Antarctica. So anyway, so that's sort of the what are the different pieces of an ice sheet and how it goes into the ocean. Now I'm going to scream through. This is a cross section. We've just finished talking about that. There's sort of the ice shelf on the right, the ice stream, and the thick part in the middle. And really the question is, how do we know that the ice sheets are changing? There are sort of three big signs that we see using three different measurements that help us know that the ice sheets are changing. They are, the edges are dropping. Okay, we shoot lasers from space, and I'll show you the data. But basically, again, you can show this with one hand. I don't even need to put down the mic to explain it this time. So the edges of the ice sheet are dropping. One measurement with lasers from space. They're losing mass. Turns out we can measure the mass of ice sheets from space. We do that with 2 different satellites. We wanted to measure her mass. The satellite would go over her, and it would get pulled down, and then it would pop back up. And then if she went on a diet, she didn't weigh as much. It wouldn't get pulled down as much when it went over her head. So that's what we're doing from space. So we know that, and I'll show you the data. But again, they're losing mass. But that's a different measurement. That's what's very cool about our observations. And when people say, how do you know it? It's like, we've measured the surface is dropping. We've measured the mass is getting less. And then the third observation is they're speeding up. Again, a different measurement. So 3 independent lines of evidence from 3 different measurements that the ice sheets are changing. So I'm just going to step you through the data. What you want to look for is places that are blue. I'm going to show you surface elevation. I'm going to show you mass loss. And I'm going to show you change in velocity. And all you need to look at is where there's blue. And all I want you to walk away with is the understanding that we have 3 independent data sets on all 3 ice sheets that tell us how they're changing. And what you can see is around the edges of Greenland, there are places that are blue. You can see they're sort of concentrated in little sort of, looks like somebody's taking a bite out of it. Here, here, here. This is one you may have heard of, Jakobshavn, Isbre. It's dropping. It's dropping up to 30 feet a year there in the outlet glaciers. The interior actually is rising a little tiny bit because since the air is warmer, there's more snow falling. But it's not balanced with the net dropping. So that's one way we know that the ice sheets are changing. The second line of evidence is remember the satellites flying over our head? Anywhere it's blue, the ice sheet's losing mass. And it's telling us the same story that where the ice surface is, the places that it's dropping the most are the same place it's losing the mass the most. So in the southeast particularly is the place that it seems to be changing the most. So same place we see the change in mass equivalent to the surface elevation. And again, we see it gaining mass in the interior because it's snowing more, but not balanced, not outweighing what's happening on the edge. And you can see why it's a complicated story. And then blue, we know it's moving faster. Blue is really moving faster. Green, it's moving not quite as fast. Not accelerating as much over the time period we've looked. So those are the 3 independent lines of evidence for Greenland. So there really is a coherent signal for the margins of Greenland. Back to the one hand, you can say it's dropping, it's speeding up, it's losing mass. Pretty straightforward and very well supported by the data. Let's look at Antarctica. We're going to do the same thing. We're going to look at the same 3 data sets. We're going to look at ice surface. So again, you want to be looking for blue. And you can see East Antarctica on the right. There's not a lot of blue there. East Antarctica is pretty high. It's pretty far away from the ocean. The ocean currents spin around Antarctica, isolating it from the rest of the world fairly effectively. Except 2 places, the Antarctic Peninsula, where we see the greatest changes in surface temperature anywhere on the Earth. They've gone up 4 degrees Celsius over a 50-year time period. And then the other place we see significant change is in this place that's called the Amundsen Sea or Pine Island Glacier, or we call it, colloquially, we call it PIG. I really prefer Pine Island. There are no pine trees. It's named after a boat that went there that was called the Pine Island. So no pine trees. But it's called Pine Island Glacier. But you can again see this is where the biggest change is. You can see it's not going down as much as in Greenland, but it's still going down. And remember, here we're a little more worried about it because this ice sheet's below sea level. It's more susceptible to warming from the ocean at the bottom. So that's this surface. Here's the mass loss. You You can see again, East Antarctica, it's kind of hard to tell what's going on. There's some yellow blotches, there's some blue blotches. It might actually be gaining mass, although that's one of the things scientists argue about, what that big yellow blob in the upper right is. But again, you can see it's very clear in the same place we were looking at, the place with no pine trees, it's very blue. We're losing mass here, as are we up on the peninsula. And the peninsula is where that Larsen B breakup was. So again, we're seeing the same dropping, losing mass. And now let's just look at the speeding up. And you can see East Antarctica, again, not much is happening in East Antarctica. Yellow, brown, it's a little baby bit of blue, but not much. But again, Pine Island, you can see it's speeding up. It's losing more mass in this area. So what's the summary in Antarctica? West Antarctica is very clear. There's a coherent signal of net mass. The ice sheet's dropping, speeding up, losing mass. East Antarctica, there's no well-defined change. So that's, if you guys learn nothing else, then I'd be just thrilled if you could, if somebody asked you, do you believe in climate change? The answer isn't belief. The answer is there is very strong evidence that the ice sheets are changing. The edges are dropping, they're speeding up, they're losing mass from 3 different measurements. That's my answer when somebody asks me, do I believe in climate change? So I have -1 minute. So I'm going to just show you the way I like to think of what's the impact, because I like to bring it back to people's, where the ice sheets are off the maps most usually, right? When we go to a Mercator projection, you slice Antarctica off the page and Greenland looks like it's as big as South America. So there's this nice website where you can actually go in and see what sea level will look like at different places. So this is New York, New Jersey, 1 meter, just zooming it in. And then that's 6 meters. Kind of fun to see what losing an ice sheet would do. And then I tried to do it for here. This is San Francisco, 1 meter. That's 1 meter. So 1 meter does a lot in this area. And then that's 6 meters. And we're going to zoom in. Here's 1 meter. Oh, no, that's now. And it has some pixelation, so you can see some places look a little blue that aren't. This is 1 meter. And this is 6 meters. Right. See, it's kind of, we can make sure you get this URL where you can go around and mess with it, sort of to see, because you can zoom in anywhere you want. So that's what we worry about happening in the future. What's going on? The sea level's going up now. This is another site you can go to where you can actually go find tide gauges around the country and see how the sea level is changing. We can actually go look at the sea level curve from San Francisco since 1850. And it's going up about 2 millimeters a year and has been since. You can see there was a problem here. Probably they moved the station. But it's just remarkable. You can see the trend. There's no question sea level's going up. Same thing in New York. Just so you know, we measure that NOAA makes sure we actually measure it on both sides of the country. You see it's going up a little faster in New York. There's some variation. It's not a bathtub. We don't live in a bathtub. But I just thought I like to think about it. I need to put these things into some sort of framework. So what I like to do is I like to actually think about when these different times were. So I like to think about where the sea level was when my grandmother was born. This is a picture of my grandmother and her horse and buggy on her way to school. Or when my grandfather was, or my father was born, and that was their Model A, where my father was messing around with, I think it was an Austin, but anyway. And when my kids were born, and the car I had then, and the car I have now. So what does that mean that since then was born? That means how much the sea level has gone up since my grandmother was driving around. So anyway, we'll just step through this quickly and then we'll get on to the activity. Just because I want you to be able to walk away with a sense is that You know, the sea level's gone up this much since my grandmother was born. That's what I like to think. So that's how high it would be on her buggy. That's how high it would be on that car, whose name I do not know because I'm not a car geek, but that's how it would be on my dad's dog. That's how high it would be on my Montero. That's how high it would be on my Prius and my dopey dog. And what we don't know is what's going to happen in the next 100 years. Is it going to go up 22 inches in the next 100 years? Or is it going to go up twice that? That's really the question we're after as scientists, and we really don't know. Is it going to go up that much? I mean, to me, it's useful to put this into a framework we can understand because we don't really think in millimeters. But when I touch my knee, I can say, okay, that's how much it's gone up. And the question is it going to go up to here or up to here in the next 100 years? That's the bottom line. Anyway, so this is sort of what 22 inches in the next 100 years looks like. Double what it's been. Your question, is it accelerating? You know, and how are we going to adapt to it? So with that, I'm going to turn it over to Margie, and because I think you guys asked questions as we went along, and Margie's going to introduce you to the polar ice activity.
Great. Thank you so much.
Sorry.
No, don't worry about it. You're fine. So before I actually jump into the activity, I wanted to just do a 2-second background on this. Polar ice is actually a curriculum project that we're doing as part of a grant that we got from the National Science Foundation. So National Science Foundation funded a project called IcePod. And IcePod is about putting instruments on a pod, which is just what it sounds like. It's a long canoe-shaped pod, which will then be flown on the LC-130s, which the New York Air National Guard flies to support the polar missions. So as it flies, it's going to be collecting data on the ice sheets. And one of our goals is to try and develop some capacity among the education community to actually, use that data when it comes back. So we're working with a team of teachers to actually help us put together some baseline curriculum using some data that hopefully we can just slip out and put in fresh data as we're collecting more. And Missy is one of our wonderful teachers on that group. We have middle school and high school teachers that are working with us on this project to help develop it. And we're hoping to also kind of garner some additional support from teachers like yourselves who will be interested in actually testing this material out in your classrooms. So if in fact you're interested in doing that, it's focused on middle school and high school. I'm just going to ask if you could talk to Missy afterwards, since I know our time is limited, and maybe she could capture your name and contact information, and we'll follow up with you. We've developed 2 of them at this point, and we're going to just keep going. So today we're going to, did you show them the pod? I'm sorry. Okay. Okay. Okay, so there's the pod, and you can see it goes right off. There's a removable door that fits on the back of the aircraft, and it can be lowered, and then the equipment would go into this particular pod and actually just passively capture information as the plane is being flown. So it's so much less expensive than actually putting a team out there to do research. So you can see why this is a really positively received proposal.
And our long-term vision is that this would be producing data that would allow the data could be used by classes similar to the activity we're doing today.
Exactly. So we can just pop new data into it. Great. So you guys have copies of this actual activity in your binders, but I don't need you to go there yet. You're such good teachers. You all immediately grab the material. What I thought I'd do is kind of walk through some of the background, and then we're going to spend our time doing the lab activity, which is way more fun, right? Yes, that's what I thought. Okay, so the activity itself is developed, I like to think of it as a standalone, i.e. there's background material already in it. So it leverages itself easily into whatever curriculum you're teaching. We're thinking that it would work in environmental science, it would work in any kind of earth science, anytime you're talking about climate polar regions. I think this will slide in easily. And again, the background is there on the glaciers so that you don't have to worry that you haven't taught that yet. It's all nicely, we think, nicely integrated into the material itself. There's also a PowerPoint, which I'm going to just really fly through, that has just it's like 14 images or something that you can use to set the stage with your students. So let's say you wanted to send home part of this as homework and they do it on their own. You could open it with the PowerPoint in your classroom, send it off, they could do it for homework, come back, and then maybe you could do the lab as a classroom activity. Or maybe you just want to kind of give them a taste of it quickly with the PowerPoint and then have them do the activity in class. Either way, or you could not do the PowerPoint. But anyway, these are the options for you. So we'll just kind of go through the background. This is PIG, what Robin was talking about, and you can see this is the floating ice shelf. Isn't that a gorgeous picture? So one of our grad students got this just this year. So, and I call it PIG because I think that resonates with students. I don't know. Pine Island Glacier is wonderful, but there's just something catchy about PIG that students seem to like. So it launches right into what is a glacier? You know, all the basic things that you need to know when you're thinking about a glacier. How do they form? How do we have them gain mass, lose mass? All of that basic information that Robin's already covered with us this morning. Then it kind of reinforces this idea that glaciers are constantly on the move. So they're not this just stagnant block of ice. They're in constant motion, moving from an area of higher elevation to lower elevation. And I'll be fair and move to the different side of the room. So one of the things they actually do while they're there is that they pick out and mark on this image in their activity where they believe the ablation would be occurring and where they believe the accumulation would be occurring. And that kind of gets them thinking about those two terms, number one, which are key to glaciers, so where it's losing ablation and where it's gaining accumulation, and then thinking about that whole process. Then we talk about what are the ways that a glacier can lose mass, and that's key because the focus on this is looking at elevation on Pine Island Glacier and determining if, in fact, it is changing. So we look at the different mechanisms that can be used. The two key ones being, or the ones that contribute the most in this area would be the melt and calving. And then they can just follow through the whole glacier system itself from where we have accumulation to where we have ablation. So they can actually trace this with their fingers and kind of get the sense of that whole glacier system. And think about it as an Earth system, which is part of what we do in Earth science. Then we shift off of that background information to actually how we've collected this data. So we have our ICESat satellite, and it operated from 2003 to 2009. Actually, NASA's in the process of developing ICESat-2 right now. Their funding didn't come through so that there was a seamless transition, but they have actually filled the gap with an air flight program, which is called IceBridge, which we're a part of with NASA. And what I really want them to take away from this is how accurate this data is. So this can use lasers and measure to 6 inches. That's amazing. You know, to really think that you can get elevation at that fine a grain is just remarkable. And then we move right into PIG itself. So what they're going to be doing, the red line across the face of the glacier, is where we have a series of data that's been collected over a 4-year period. There are 3 different time series that they're going to be looking at, and they're going to be assessing if there's been any change in the face of this glacier. We show them where PIG is. So Robin already has pointed this out, but it's, you know, right here in this little catchment on the West Antarctic ice sheet. And isn't this a cool image? This is the new bed map image, which is with the ice sheet removed. Isn't it beautiful? From Antarctica. So again, we can locate them. We can show them where it is on Antarctica. And then this image is key in terms of looking at where the ice shelves are. So ice shelves, as Robin mentioned, are something that helps to hold the ice back on the land, on the continent, and keeps it from accelerating into the ocean. You'll see there are all these ice shelves that have been located around Antarctica, but if you look, you don't see one on Pine Island Glacier. But we saw a picture of one at the very beginning. So what's going on here? Well, basically, the ice shelf is so small that it just isn't going to get registered on this larger image. So they actually calculate what the size of this ice shelf is for Antarctica, and it's about 800 square kilometers. So much, much smaller than all these other ice shelves that are shown here, which hopefully starts giving them the clue that maybe there's a connection there with this small ice shelf and the fact that we might be losing elevation at Pine Island Glacier. So is pig a climate canary? And Robin mentioned to me, I don't know if they're going to know what a canary is, so I put the definition down here as to why we would call it a canary. And he's got on his shades to block out the albedo. So at this point, they're ready to launch into the activity. And so I'm just going to, we'll talk through this and then we'll let you do part of this activity. So this is the data that they're going to work with in the first part of this activity. The kilometers are listed in the first column, and then we have 3 different sets of elevation data. And you'll notice, I'm sure there's somebody that's going to say, why do you have November, April, and October? Those are not equally timed events. Why wouldn't you have 3 that are all the same? And so what I want you to think about is November and October in Antarctica are going to be your spring-summer. Okay, it's going to be the reverse of here. And April is going to be more in your winter. So if you think about it, you would expect that, if anything, you would have higher elevation or higher accumulation in your April time series. So that's something that we want them to be thinking about and looking for. Do we actually have an increase with this different time series, or is everything starting to go? So again, it's not kind of a fun thing to point out and let them look at. So I'm not going to have you plot this right now. We're going to have you plot the next one. I'm just going to show you what happens when you put it all out there. You're like, that wasn't very exciting, was it? Doesn't look as if anything's going on. So why did I bother to just plot all this data? So how could we do this differently and have it have an impact? How could we really see what's going on? So the next thing that we do is we actually take the 2003 data as our baseline. So we're going to actually look at the delta, or the difference, against 2003. So that's what we're going to have you guys do now. So Missy has papers that we're going to pass out to you. You have this data series on the front page, and there's a piece of graph paper that's coming around to you. And what I want you to do is actually graph this data. Your x-axis is going to be the kilometers. And then what you're going to think about is the data that we're graphing is all negative. So you're going to want to set your 0 line high on your graph, right? And then you can just draw a line across and label that just flat old 2003, because that's our baseline. And then we'll graph beneath it with the negative. Does that make sense? Anybody have a question about that? So I don't want to lose a whole lot of time on this, because primarily this was just to get you looking at and thinking at the numbers. And for those of you who found this confusing, I think that if you had actually walked through the exercise as a student would, going through the whole thing, it might have maybe leveraged itself better in. What I thought I'd do is actually just show you how it graphs out so that we could look at it and talk at it. Oh, I know, I'm sorry, I'm ruining it for all you guys that are so careful. But I'm a little worried about time, and I wanted us to get a chance to actually play with the lab and the glacier goo. And so if you don't want to look up, don't look up. Bury yourselves back there. But for those of you who are interested in instant gratification, I have popped up the graphs showing the delta. And so I really want to point out to you, you can plug your ears too if you don't want to hear this, but the April 2007, you'll see where we thought we might actually have a gain, because that's the winter, right? You don't see that, do you? You actually see that we're losing elevation. Okay? And you'll see that there's a big drop in elevation kind of right down the middle. And that's because, why do you think that is? Does anybody know? So glaciers tend to have more friction along their edges. The ice streams do, where they're kind connected to the more solid ice. And so the center is going to move faster. And actually, if we had more time and a different setup, we could actually do that with the glacier goo. And you could watch that the edges will actually have more friction and slow down, and the centers will move more quickly. So you can see that between... Oh, and I'm sorry, I have a typo on here. This should say November 2003. Between November 2003 and April 2007 and October 2007, we're definitely losing elevation. This looks a whole lot different than the last time we graphed it, right, where you couldn't really see the differences. Okay, so what we thought we'd do now is actually, now that you've thought about this a bit, looked at a little bit, we would actually move right into the lab. So if you flip over, you have the lab packet in front of you, and the lab itself is broken into a couple of different pieces. Our expectation is that you wouldn't do this all in one day, so that the lab might be done separately from when you do the first part of the activity. And therefore, the very first part is kind of getting them thinking about glaciers again. So thinking about how glaciers move and that glaciers do move. What we'd like you to do is start with, on that first page, start with questions 3 and 4, because that's the basis for the rest of the lab. So it says, could an increase in ablation on a glacier cause a change in elevation? And why? Or explain your answer. And then the next thing is, looking back at the data you graphed for pig, which is right in front of you, what hypotheses could explain the changes in the pig glacier? And that hypothesis is what you're going to actually be testing in the first part of the lab. So if you just take a second and write down what your hypothesis would be, then we'll launch into playing. The hypothesis is looking back at the data you graphed for pig, write a hypothesis that could explain the changes in Pig Glacier. So what could explain the changes in Pine Island Glacier? So if you look at, this is like an ice stream. So this is a glacier, and this is where it's moving quickly. And it's collected across the face. So it's a line of data across the face.
Where roughly does the ablation occur?
So the ablation occurs, well, the ablation occurs through the upper end of the glacier. Accumulation happens up above. You have what's called a zone of ablation, where ultimately you're losing more than you're gaining, right? And it happens in different places on different glaciers. And as climate is warming, a lot of these zones of ablation are actually moving higher and higher up, okay? How do we do? So you have wind that would actually reallocate this. You have sublimation, where it's actually going straight into vapor. You have calving, where it's kind of moving off in sections, and you have just plain old melt. So you have all 4 of those going on. So the data was collected, right. So it was collected, though, in the, yes, right around in the transition. I think that's where I confused myself when I answered you. I didn't make it very clear at all. Okay, so this was supposed to take a very short period of time. We want to get in here and do this activity. So, no, it's great. I have 14 setups back here. They each have a packet of glacier goo. You have a little collection container. You'll have a ramp that has a measured section on it, which you will be using later in the activity. And I didn't bring stopwatches and calculators, but I'm hoping that we have enough people with smartphones. Right. So find yourself a smartphone person if you don't have one yourself. I think with the numbers that we'll have either 2 or 3 working on a 2 or 3. But I'd like to get them all in use because I brought those darn things all the way from New York. So let's use every one of them. Okay.
Oops, sorry. Sorry. Oh,
I do
it's under number 2.
Yeah, we
You have the
interesting. It still has the text up here at the top. Yeah, because you want to start it at the start. So but it's starting.
Yeah, we want to.
But
So you know what? So what we're going for here is earlier part of this activity that they move under their own weight. So they just move as part of gravity, and that will be something that they can actually look at and see happen right here. So that's the kind of connection between this
Well, I guess
and the
they're
real
asking
world.
us to start the.
That makes a meter down and your toe following here, and that's really your baseline
I want
condition.
some of this.
Okay, so the toe supposed to that's
So we mark the top.
Silly puddle is what it is.
and then you
Yeah,
would
just a
measure a
little bit
centimeter
more
down on the side.
Fluid, yeah.
And so the idea
Okay, so
is
I need
then
to
you
measure
can
that height.
return to this and see how long, see what happens to your surface. You're using your markings on the side, and one thing you have to be careful of with this is that the edges stick, so you just need to take your ruler and take it to the back of your surface and see what happens. So basically, can you see that there's